An event, as you remember, is just a set, and the relationship and result from elementary set theory can be used to study events. Remember that the complement of an event is denoted by A prime. We frequently use A bar or A complement in replace for A prime as well. It is the set that is not including elements of A. So here you have set A, and everything else is in the complement of set A. So as you can see, A union, but its complement is equal to the sample space or the universal set. The union of two events or two sets denoted by A union B, A or B, is the event consisting of all outcomes that are either in A or in B or both. And finally, we talked about the intersection of two events or intersection of two sets, which is denoted by A intersection B, A and B, which includes everything that belong to the intersection. But these are the visualizations that we saw for union and intersection. Finally, if you have a universal set or if you have a sample space, including A, B, C, D, E, F, G, if you take different events from that sample space or taking some subsets from the universal set, we can form the union, intersection, the difference, and the complement. Basically, the union is everything that is in both sets. B minus A is everything that is in B but not in A. A intersection B is all the common elements between A and B. And finally, the complement of set A is everything that is not in A. Empty denotes the null event or empty set. This event consisting of no outcomes. If the intersection of two sets is empty, we say that they are mutually disjoint. We saw an example about the car dealership, and we discussed two mutually disjoint or exclusive events as well. Now, for the classical or theoretical probability, it is used when each outcome in a sample space is equally likely to happen. When we are dealing with the probability of an event, it is the number of outcomes in that event, n of E, the size of that event, divided by the size of the sample space or the cardinality of E over the cardinality of the sample space. Or in some books, you might see n of E divided by n of S. Given an experiment and a sample space like S, the objective of probability is to assign to each event A number, P of A, that we call the probability of that event. So the probability of an event in short format, mathematically written as n of E divided by n of S. We have some axioms for the probability function. If S is a sample space, a probability as a function P from set of all events in S to the set of all real numbers has the following axioms. That function always have an output which is bounded between 0 and 1 inclusive. So the probability can be 0 or 1 and any number in between. The probability of empty set is 0. The probability of sample space is equal to 1. If you have two disjoint events, the probability of their union is the probability of first set plus the probability of second set, or the probability of first event plus the probability of second event. We can also generalize the idea. For any event like A, P of A is always positive. So this function cannot be negative. The probability of sample space is equal to 1. And if you have infinite collection of disjoint events, like A sub 1, A sub 2, A sub 3, A sub 4, and so on, then the probability of their union is equal to the summation of their probabilities. So this guy can be written as the probability of A1 plus the probability of A2 plus the rest of the probabilities. And as we saw, if we have a null event, the probability of empty set or null event is always 0. For example, we can just verify these axioms for the following experiment. Consider tossing a coin or consider tossing a thumbtack in the air. You have two possible outcomes, up or down, head or tail. The sample space has only two outcomes. The probability of S, which is n of S divided by n of S. Remember that when you're talking about the probability of sample space, this is n of S divided by n of S. You're dividing the same number by itself, which is 1. And the probability of up, down, they are disjoint events. There is no intersection between them. So basically using the third axiom, the probability of U plus probability of D is equal to probability of sample space, and we just showed that it is equal to 1. So again, the probability of S is equal to n of S divided by n of S, which is always 1. To find the probability of the complement of an event, we have the following rule. If A is an event in sample space S, then the probability of its complement is 1 minus the probability of that event. Basically saying that, hey, if I have a universal set, A is just right here, its complement is everything that is not in A. You want to show that since these two sets are disjoint, the probability of the complement is equal to 1 minus probability of A. We know that the intersection between these two sets is empty. They have nothing in common. And if you take their union, the union is equal to the sample space. Well, since A and A complement are disjoint, the third axiom says the probability of A union, the complement, is equal to the probability of first set plus the probability of the second set, which is equal to the probability of the sample space, because they are forming the sample space. If you take the union, it is equal to the probability of sample space, which is equal to 1. So far we have the probability of A plus complement is equal to 1. If you subtract the probability of A from both sides, the probability of complement of A is equal to 1 minus probability of A. So as a rule, the probability of A complement is equal to 1 minus probability of A. You can also write it this way. The probability of A plus probability of A complement is equal to 1. Or we can write down, hey, the probability of A is 1 minus the probability of its complement. Just basic algebra, going back and forth between different notation, different representation here for the probability.